Howdy YouTubers, this is Nick. I have a little bit of an experiment going. This is my relatively new Rigol oscilloscope, and what I've done is, if you've seen my Instructable, which I'll link to below, I've set up an experiment where I'm going to compare the 60 hertz electricity that we get here in California, compare its long-term stability of its frequency against GPS. So what I've got here is I've got, first off, start by getting a 9-volt AC transformer that's been commercially made and UL approved. Don't go poking oscilloscope or voltmeter probes in your electric outlets. That's not the right way to do it. You get a nice 9-volt transformer and you'll be dealing with stuff that's very safe. This, I'm just feeding the output of the transformer. The one leg of the transformer has been grounded. The other one is swinging. It's a 9-volt transformer, but that's RMS voltage. So of course it's swinging more like plus or minus 14 volts if you do the math. So it's about a 28-volt peak to peak. And that is the yellow trace, that's channel 1. And channel 2 is getting a pulse per second output from a GPS receiver. Now, of course, GPS is, this particular model, the GPS is accurate down to about 10 nanoseconds, apparently. For our purposes, it's going to be used as our standard. You know, you can argue about the long-term accuracy and stability of GPS, but you got to pick something, and it's the best bang for the buck for the experimenter in time is GPS, because it's so cheap relative to the accuracy you get. But as I've been watching, or excuse me, as I've been filming this, if you're watching, you'll see that the blue trace, by the way, that's the GPS pulse per second. It's also the trigger point, so you'll see that that's not moving. And it's not moving because the oscilloscope is set to trigger at that point. You'll see that there's that little yellow T triangle right above the rising edge of that wave that's letting you know that that's where the scope has decided to set the trigger. And I've moved the trigger point over a little bit so you get to see the whole thing. It also makes a nice marker so you can see the movement of the AC frequency relative to the GPS pulse. And now you can see that it's shifting just a little bit to the left. I've also seen it shift to the right. The point of the Instructables, of course, is to get a long-term count of how many cycles, one way or the other, ahead or behind, the AC current is from GPS. The hypothesis of the experiment is that over a long enough period of time, the long-term cycle debt, which is what I call the actual number of cycles of AC current versus expected over time, the long-term cycle debt should be 0 because the utilities should, or at least the central grid operator here in the West, and again there's 3 in the United States, there's the East, the West, and Texas. Texas has their own frequency domain for historical reasons. But in any event, out here in the West, which is what California is, the long-term cycle debt should be 0 because they should be disciplining it at least to GPS, if not to a rubidium standard or something like that. But I wanted to catch this video because you can at least see very distinctly the motion, when it's in motion, of the phase of the incoming AC current versus GPS. And I'm going to probably run my experiment for at least a week, probably just a week, and I'll try and come up with some daily plots of the accumulated cycle debt per day, and maybe over the course of the whole week, and see if that comes out to be something interesting. So thanks, and talk to you later. Bye.